This is a talk about my recent effort in training a really large language model on our supercomputer that is Frontier. So the unique thing about Frontier is that it's built using AMD GPUs. And as you know, most of the deep learning or LLM training frameworks are custom made for NVIDIA GPUs. So there have been some challenges how to run those frameworks and all this existing research on AMD hardware. And also, we wanted to see how to actually train a model that is of size 175 billion parameter model and finally a trillion parameter model. And that was pretty challenging. So we had to figure out the right strategy so that we could scale up to such a large model. I have been doing some research on training large language models and deep learning models in general on our uh, supercomputers. So I work in a national lab and also a supercomputing facility where we host usually the fastest supercomputers in the US. So recently I've been working on Frontier, and Frontier is an AMD GPU built supercomputer. So we have around 75,000 of them. So of course, once you have so much compute power, the natural place you would think nowadays is train a really large model on that. But as you know, that most of these training frameworks or all this research, they have been implemented using NVIDIA GPUs. So there have been some challenges. How do you actually run this on on GPUs from a different vendor? And also, it's a new platform, all these new communication technologies and everything. So how do you actually train the models on these our new supercomputer efficiently? In this talk, I'll try to give you some ideas or my understanding about how to train large language models in general, and also pinpoint to my experience on how to train these models on our system that is Frontier. So I kind of thought about outline that initially I give a brief overview of large language model internals that's necessary for understanding the challenges of training them. That's based on distributed training paradigms such as data parallel and a few model parallel techniques. And then the pivotal thing about my talk is that actually about the search for right strategy to train the large language model on our system so that we actually get decent enough throughput and scaling efficiencies. And finally, I'll share the recipe for training a large language model up to a trillion parameter on our system. So what I found is that most of these findings or recipes are actually translatable or useful for other clusters too. You just have to be mindful about the nuances in their node architecture and whatnot. To start with the transformer architecture, you all know this diagram from attention is all you need. So that's a transformer which has a stack of encoder blocks and a stack of decoder blocks. And most of the GPT-like models, they actually take the decoder blocks and stack them together to make a really large language model. So, for example, GPT-3 is 175 billion parameter model. And GPT-4 is rumored to be more than 1 trillion parameter model, but with sparse connections and whatnot. So just to kind of like show you the two families of transformer models that people use, BART based on the encoder part and GPT on the decoder part. So to know how much challenge you actually have to face in terms of how much memory you need, how much compute you need. So let's kind of focus on the parameters that this transformer block introduces. So for the attention part, you need three weight matrices, W, K, Q, and V. And then you compute the attention that goes forward through add and norm. And then you have feed-forward network, which has two layers. First one is a D by 4D weight matrix. Second one is 4D by D. So as you can see, it's like a regular artificial neural network, but here you have this bunch of weight matrices that you have to run through in the forward pass and in the backward pass. So ways to update are these five matrices, at least for the vanilla transformer. So now you kind of like know how the transformer model looks like, and let's move to how to actually distribute train them. So we all know the data parallel training is probably the most simplest one when your model fits within a single GPU. So your challenge is more like fitting large data. So you can split the large data, let's say, into parts. And let's say if you have three GPUs, you replicate your model 3 times and try to parallelly process each part of this data batch on each of these models. So only thing you have to make sure that at the beginning of every training iteration, all the training parameters across all these replicas are the same. Now coming to see what's different about our hardware or the Frontier's node architecture. So on Frontier, we have around 9,500 nodes, and each of these nodes actually has 8 AMD MI250X GPUs. So there's a little bit of heterogeneity when the GPUs are within the node, and even there when they're in the same die, you can see they have like four interconnect, and those connections are Infinity Fabric. So it essentially gives you around 200 gigabytes per second. But when the GPUs are connected across, they give lower speed. And whenever you need to send data from one GPU to another GPU from another node, you have to go through the network card and Ethernet cable. And Ethernet cable is much slower compared to this Infinity Fabric, which is 25 gigabytes per second. So this would become handy whenever you decide to do model parallelism and put different parts of the model in different GPUs across nodes. You want to make sure that you don't incur too slow communication across the Ethernet cable. Why we need model parallelism actually stems from the number of parameters and memory requirement. So here, a transformer layer, the attention layer has 3D square parameters, and the FFN layer has 8D square parameters. So you can see for a single layer, you have around 11D square. And if you add up the front matters like embedding layers and everything, so for a transformer with L layers and D hidden dimension, you can expect there will be 12 LD square parameters. So these parameters need storage because you have to save those variables in the GPU memory. And if you do mixed precision training, so you have to save 6 bytes per parameter because 4 bytes is needed for saving the full precision copy, 2 bytes for intermediate half precision training. Then you have the gradients that requires 4 bytes per parameter. Optimizer states you need mean and variance. So you need 8x, so 8 bytes per parameter. And if you think about the activation intermediate values, it kind of like comes down to for one parameter, you need around 20 bytes of GPU memory. So what that means is that if you want to train a 22 billion parameter model, you will need 440 gigabytes of memory. That's the minimum. And for a 175 billion model, you need 3.5 terabytes. And for a 1 trillion parameter model, you need 20 terabytes. So, but the GPUs that we have, or I have worked on, they have only 64 gigabytes in each of these GPUs. So you can see these models are actually too big to fit in a single GPU. So definitely we need to break this model apart and place them in different part of the GPU. So different GPUs will host different part of the model. So it's kind of like this art form, kintsugi, where you kind of like, if you break a vase or a pot, you reconnect them, but probably with some golden plating and whatnot. So here the analogy is a little bit stretched, but what I like about this is that whenever you break a model, you also have to piece them together again. But here, when you piece them together, you incur some cost in terms of communication because the data needs to travel through the communication channel, and depending on what part of the communication channel is traveling, it might incur some latency. I'll try to answer any questions that I notice, but I can also answer questions towards the end. So for model parallelism, I think the most simplest one would be tensor parallelism, where you, if the model is too large to fit in GPU's memory, that's the motivation for all sorts of model parallel. But the idea is that, so let's say you have this model with 4 layers, and you know that the whole model is too large to fit in the single GPU's memory. So you slice them with, let's say, these horizontal lines, and take one slice and put this one GPU, second slice, second GPU, and so on. So whenever you want to, let's say, in the forward pass, you want to compute the layer 1, so you can send the same data across this slice, this part, and this part. And at the end of these computations, you need to do an all reduce to bring back them together so that the result is aggregated. You have to do this, and you can see this is happening after every layer. I took this diagram from Megatron LM paper. So the idea is that they're using kind of splitting the parameters into two parts, then putting them into two GPUs. At the end of each layer, you actually have to do an all reduce operation. So that's kind of like the standard for transfer parallelism. You slice the model, put them into different GPUs, but then at the end of the forward pass, you have to bring them back together through an all reduction operation. This same for the FFN of the transformer. But when I was trying to use transfer parallelism, because it's kind of like much simple to understand and utilize from Megatron LM code base. So the challenge is that how much or how many slices you actually want to break the modeling down. So if I use transfer parallelism to 4, that means 4 slices. Let's say I'm getting per GPU throughput around 60 TFLOPS. When I move to 8, it moves to around 50, and when I go to 16, it moves to 25. So the lesson here is that when you're using up to 8, that means you can slice the model and still can feed them across the GPUs within the same node. But still, with increasing number of TP, you're incurring more cost, communication costs is going down. But whenever you actually have to cross the node boundary, so 16 GPUs means 2 nodes. So now 2 nodes are hosting the different parts of the same model, and they have to travel through the Ethernet cable. So that's why this throughput falls much faster. So that's why you kind of like don't want to use transfer parallelism more than 8 or whatever cluster you are using. You have to look at the number of GPUs within that node. And if you see that the number is 6, 8, or whatever, you don't want to cross that number. Transfer parallelism, if you are not allowed to slice the model into more than 8 parts, so you might not be able to feed the entire model. So for example, for a 1 trillion parameter model, I probably need around 512 GPUs. And if I can only slice them into 8 parts using transfer parallelism, so that's not good enough. So another way to partition or slice the model is to layer-wise. So you group consecutive layers into different pipeline stages and put them into individual GPUs. Then you break down your batch into micro batches and try to pass micro batches one at a time. So this is the method that gpipe uses by Google. So you break a single batch into 8 micro batches, and you have, let's say, 4 device hosting 4 pipeline stages. So the first micro batch will go to the device 1, and at that time, other devices will be idle or other pipeline stages. But whenever the one is moving, device 1 is ready to process the micro batch 2, at this time, device 2 is ready to process the micro batch 1. So you can see this is kind of like it's moving in a stepwise in the forward direction. And when in the backward propagation, it again does the same. So this is kind of like you're doing the compute and communication overlap, but that actually incurs some computational bubble. So there's some better strategy. For example, this 1F, 1B scheduling. So here you first select every GPU or every pipeline stage to see the first micro batch, but then you make sure that every forward batch, micro batch is actually followed by a backward propagation micro batch. So that way, kind of like reduce the bubble size. And a further strategy is to you do this pipeline staging into more granular way, and then put multiple pipeline stages within the same GPU so that the GPU is kept busy most of the time. So the whole idea is to kind of reduce this computational bubble where the GPUs are actually staying idle. And this is kind of straightforward to quantify because the formula for micro batch, say bubble size or the GPU that being idle for some time, that's actually number of pipeline stages divided by number of micro batches. So I did some experimentation for 22 billion parameter model and 1 trillion parameter model. So if I fix the number of pipeline stages, but then keep increasing the number of micro batches, so I see that the throughput actually goes up. I mean, eventually it saturates, but the indication is that if you can use a really large global batch size or really large number of micro batches, pipeline parallelism can give you good relief on the throughput deterioration. And also to verify this formula, if I actually increase just the pipeline stages while don't increase the micro batches, I see that the throughput actually goes down. So you have to be mindful about this pipeline bubble size, and you can maintain the performance throughout this thing if you increase both of them proportionally. So if you increase the number of micro batches, you should also increase the number of pipeline stages. So another thing is sharded data parallelism. I don't go too much into this. It's kind of like starts like a tensor parallelism. You slice the model, put them into different GPUs, but then you want to emulate it's doing the data parallelism. So because the GPUs are not big enough to fit the entire model, but they might be big enough to actually feed entire layer at any given time. Just to go very shortly, very briefly, so let's say each of these GPUs have these one slices of these models, but at time step one, everybody should have the layer one. So what they can do is they can borrow the missing pieces from each other through an altogether. So as you can see, they have their own slices, but on top of that, they materialized layer one the first time using the altogether. So now they can actually do the data parallel training, at least for this layer. But then when these layers work is done, they can delete the parts that they borrowed from the other GPUs and go for the second layer. And again, reconstruct the second layer and so on and so forth. For our experimentation, we used 0, 1 from Microsoft DeepSpeed. You can also use fully sharded data parallelism, which is developed by FAIR, but it's also part of native PyTorch now. So now that we have all this parallelism, but how do you actually kind of combine them together to train a really large model? These are the limitations that we identified. Don't go more than 8 for TP. For pipeline parallelism, use large number of micro batches. And for data parallelism, you cannot really use too much of data parallelism because that will give rise to large global batch size, which will bring down the accuracy of the model training. So in a way, it's kind of like 3D parallelism that was introduced by, I think, Microsoft and NVIDIA together when they combined Megatron and DeepSpeed code base together to have this Megatron DeepSpeed. But the idea is that if I use all of this parallelism together, and what are the right mix of these things? So I define this hyperparameter search space, let's say pipeline parallel size. This is for a 175 billion parameter model. We did same thing for the trillion parameter model. So let's say TP belongs to 1, 2, 4, 8, 12, or 16. Because 175 billion parameter model is at least it's not too large to fit in small number of GPUs. So we could actually fit them in the, let's say, 64 GPUs. But then you have to distribute this 64 across PP or TP. So that's why I have these enumerated some discrete values, and I want to try these different combinations to see which one actually gives me the best GPU throughput. These are the hyperparameter that I am looking into. Usually when people do hyperparameters search, they actually look into for the model's training accuracy and whatnot. But here my objective is to actually look into the training performance in terms of computational performance. Is it giving me enough throughput and whatnot? How does the 3D parallelism looks like? So for example, I previously showed you, you can do vertical slices and horizontal slices. But let's say you have 8 GPUs and you want to actually slice them into 8 parts. So you can do this kind of like multiple dimensional slices and take each of these slices into individual GPUs. So here you're mixing tensor parallelism and pipeline parallelism together. But then let's say you also want to introduce data parallelism on top of that. So you can replicate what I had here and put this into 2 other nodes. So you can see that you can slice and dice the models in at least in a couple of dimensions, and then you can replicate for data parallelism. To facilitate this whole thing, we wanted to try out some existing code base, which is Megatron DeepSpeed, that supports all of this parallelism. And this is a fork by Microsoft from NVIDIA's Megatron LM. What specifically they did is that they introduced or incorporated their sharded data parallelism, as in 0, 1, 2, 3 optimizers. And they also implemented the latest pipeline parallelism on top of Megatron LM's tensor parallelism. So yeah, this supports 3D parallelism or actually more than that. And so we wanted to use that one. But problem with this is that, as you can see, this was originally forked from NVIDIA. So most of the kernels are written for CUDA, and those are optimized for CUDA. So we needed to port this code base so that it can run on AMD GPUs. I'm not partial to AMD or NVIDIA, but the platform that we have that uses AMD GPUs, so I had to do this. So we had to make some code changes. Either most of them were automatic using PP5, but we also had to go into the code and actually do some implementation and modification so that they run on our system. So I have this code base available for people if they want to give it a try. Using that framework, and we used a tool called DeepHyper to search for the best strategies and to see which one gives me the best GPU throughput. When I did this for, let's say, this is for a small model, it was for, I think, it was for 175 billion parameter model. So as you can see, this gradually actually finds better and better combination with the better objective values. But also because we are giving lots of discrete values, and many of them actually running into out of memory errors. So it's not a super optimal, at least to the point I have used. But the thing is that it's a pretty handy tool. As you can see, it has a general trend of going up in terms of objective values. And this is actually under the hood, it's a Bayesian optimizer, but we had to create lots of slurm jobs dynamically based on these parameter combinations and see which one gives us the best performance. We did a sensitivity analysis on these different parameters. It looks like micro batch size is the one of the major contributor in the performance, then the tensor parallelism, pipeline parallelism, and number of nodes to fit a single replica. And the final one was whether we use the sharded data parallelism or not. Honestly, in my experience, I did not see much difference for a large model if I use 0, 1, or just a vanilla distributed data parallel. Combining these all together, we actually tried to train some large models. So we tried to train large models of size 175 billion parameter and 1 trillion parameter model. Few disclaimers, we did not train the models till completion. Completion in the sense, you train the model on 20 times more of the data than the parameter. So for 1 trillion parameter model, ideally you want to train them on 20 trillion tokens. But we mainly wanted to establish a workflow or how to train this model. So for some test runs, we trained these models up to a few hundred iterations. But for reporting numbers, I trained the models up to 10 iterations because I saw that the training performance in terms of throughput and everything becomes steady after within these 10 iterations. Yeah, we don't have any released models for this, but we have this pipeline and the process where we can actually train the model, and we have these intermediate checkpoints. So what we have found for the best parameters for training a 175 billion parameter model and a 1 trillion parameter model is that for 175, you use TP4. For 1T, you want to use TP8 because otherwise it's too much pressure on the pipeline parallelism. So you can see for trillion parameter model, we are using 64S pipeline stages. We are using significantly large global batch size so that we can accommodate large number of micro batches. And another important thing is that flash attention. So we worked with AMD folks, and also we had to do some code correction on our end so that the flash attention actually runs on our system and produces correct output. So flash attention actually was a kind of like a game changer because I saw that it gives us around 30% speed up boost on top of whatever we had. So yeah, and we also, of course, use checkpoint activations, and we trained the models on FP16. FP16 and BF16 perform similar, but training probably is more stable when you use BF16.
You didn't train the whole model because it's expensive, or what was the reason?
So it's actually expensive in terms of, let's say, if I want to train the model on 20 trillion tokens, so our estimate was that with this current throughput that we are getting, we'll need to use our entire frontier supercomputer for almost like an year. So using a supercomputer for a year is a little bit impractical for us because this is mostly used for science applications. But if we wanted, we could actually train the 175 billion parameter model because it would only take a few weeks, and which is doable. That's kind of the reason. I mean, we could do this, but then it's kind of like it came down to decision making. Should we actually go through this? And also it would need lots of higher level approval and whatnot. The main metric that I was looking into, so our MI250X GPUs, each of them actually has this theoretical peak of 191 teraflops that you can theoretically achieve for half precision computations. With our benchmark, we probably could go up to 60% of that. for regular matrix multiplication operations. But when it comes down to deep learning LLM training, you know that there are lots of non-linear operations like softmax and everything. So it's kind of like hard to match the 60% or 70% performance of the linear algebra libraries. But for 22 billion parameter models with all these optimizations and hyperparameter tuning, we could achieve around 38% of the peak throughput or 73.5 teraflops. For 175 billion parameter model, we got 69.2 TFLOPS, and for a 1 trillion parameter model, we got 61.2. So you're seeing that it's going down, but it's mostly because the larger the model, the more GPUs it involves, the more communication over Ethernet it incurs. So that's why the throughput is going down. But still, for a first effort, we are satisfied with the throughput that we are getting, and we believe that with some further optimizations, we can improve the numbers much better. Next thing was that we did some weak scaling performance. That means we kept increasing the batch size, global batch size. So, and using that from 128 GPUs to 1024 GPUs for 175 billion parameter model, we could see that our weak scaling efficiency is 100%. Same with the 1 trillion parameter model, where we went up to 3072 GPUs. We saw that we can get to 100% weak scaling efficiency. But the caveat is that for this weak scaling efficiency, every time you create a new replica of the model, you also increase the global batch size. And increasing the global batch size is not sustainable after a certain point because the training accuracy actually drops. It's a known issue about large batch size training. More practical thing to look into the strong scaling performance. Here, let's say I'm fixing the total batch size to a fixed number because this is the maximum that I can actually go without sacrificing the accuracy. So here I chose a value 8,000 because in a previous work by our team, it's called Forge model. So we trained our model up to 8,016 sequences. So I have not seen anyone using larger batch size than this. So in a strong scaling efficiency, so now we are increasing the GPUs. That means, but we are fixing the batch size. That means we are using more and more GPUs to fix just one single copy of the model. And if we do this, we see that the strong scaling efficiency for 175 billion model actually drops to 89% on 1024 GPUs. And for 1 trillion parameter model, it drops to 87% on 3072 GPUs. So, I mean, HPC workload-wise, it's not entirely terrible. I think it's still kind of like something to be hopeful about. But the further indication is that, let's say if I want to use 10,000 GPUs or 20,000 GPUs, so this strong scaling efficiency probably will go further down. So that's also a limit because if you are not allowed to increase the global base size arbitrarily, you have to draw a line how many maximum GPUs you can actually use. That's kind of like a, a sobering truth, but at the same time, a good rule of thumb, like before you throw in thousands of GPUs, you know what is the throughput rate of you are actually getting. We published this paper on archives, so you can take a look in there. And this also recently got accepted at ISC so I'll be presenting this paper in Germany, Hamburg in May.
So in terms of like dollars, how would you compare the cost of training on, like, say, NVIDIA GPUs versus the HPC cloud, AMD HPC cloud that you used? Is it cheaper or same cost?
That's a really interesting question, but also a pretty hard one to answer because we know that we have the cloud resources that provides with NVIDIA GPUs. Actually, our lab recently did compare 3 clouds against our 2 of the supercomputers for various workload. So there, I don't exactly remember the cost, but I thought the cost was comparable. But for our case, because we have actually AMD powered supercomputers, so we don't have the cloud, and I don't have the cost breakdown of that because we get to use by node hour. But from that paper, where we evaluated cloud versus the supercomputer, that kind of like showed that the costs are kind of like comparable.
Thank you, Sajal, for this presentation. A quick question. Could you please share some strategies that you might have applied for preventing data leakage, for example, when combining weights from different GPUs? Or do you have some insights that while going through optimizing this distributed training? Do you have any suggestions on data leakage?
I have not looked into data leakage. Can you elaborate on what do you mean by data leakage here?
So basically, when combining, let's say, weights, you mentioned, in one of your slides, then when combining weights from different GPUs, so how do you verify you're not losing any weights related information?
One thing is that we are actually, when we are communicating, of course, we did not look into the fault tolerance aspect of this yet, but our nodes failed. So of course, we can lose something. But in an ideal scenario, we are actually sending the entire data without any kind of masking, and we are assuming they are received well, and we are combining them. However, we looked into something, for example, FP16 versus VF16. So we saw that when we use FP16 on our frontier, sometimes because FP16 has a much smaller range in the small values, so it actually changes many small values to 0.
Okay.
And when that happens, we kind of see that whenever looking at the loss characteristics or the trajectory, so you see some spikes. So the training kind of takes a little bit detour and then eventually comes down.
Okay.
So we saw that using VF16 is kind of more reliable. But other than that, I mean, I've not seen any data leakage instance yet.
My question may be somewhat similar to what Akash asked. I'm just wondering, when you're slicing layers of model, right? What are the potential risks for the output of the model in this case, when you're distributing it across different clusters?
Theoretically, no, because we are actually doing exact computation. Because even we are slicing the models the way, for example, in the tensor parallelism, when we kind of divide the matrix, let's say, essentially column-wise for, let's say you have 24 attention heads, and you actually try to divide them across these 24 attention heads, and which is kind of mathematically possible without losing any accuracy. So, however, I think it's worthwhile to actually inspect, because you know that whenever you accumulate floating point numbers, and depending on which order you are actually adding them together, they might actually give you some floating point arithmetic error. So whether that has any impact on the quality of the training, I would suspect that there would be some, but I believe it kind of gets averaged out and is probably not that significant.
What sort of issues did you face while training the model in terms of fault tolerance? I know GPUs fail, or I know 1 trillion model has a checkpoint would be very large on a disk space, and there'll be data sharding issues, right? Like micro batch sizes being same, or GPUs waiting for data, or what sort of challenges did you face? And I know you didn't train the full model, but for whatever model you trained, and how did you deal with those challenges?
Face few of the challenges. For example, let's say I wanted to see what is the kind of the sweet spot for fitting a small model on a single GPU, so that I can decide what is the model shards. Like when I actually break down model across the GPUs, I should choose the number. So I saw that, okay, for 1.3 billion parameter model per GPU, kind of looks pretty good. But then I wanted to get the throughput, high throughput for that one. And I started increasing the micro batch size. And at some point, it kind of I think there might be some issues with ROCm software stack. So it was giving very non-specific errors, kind of not really saying that it's out of memory, but it's just saying that unknown error, but related to memory. So that's something I couldn't figure out, but it kind of felt like it's actually trying to access some unallocated memory area and whatnot. So that would be one thing, I think. What other issues have I faced? So yeah, sometimes the communication used to get stuck. So we have this, we use recall, but then the regular software stack, when you try to use recall as part of ROCm, sometimes it will hang and the communication will kind of just stay there for minutes after minutes, like 20, 30 minutes. So, or sometimes it time out. So to get out of this, we use this plugin by AWS. It's kind of Leap Fabric AWS plugin. And once we use that, kind of like the performance improved significantly from communication-wise, and there is no more getting stuck. Another thing is that we had to use data loader 0 or 1 because it's kind of like known issue for with PyTorch code. Sometimes when you use multiple threads for data loading along with the main driver CPU thread that is communicating with your GPU. So for some code bases or probably some version of PyTorch, that's also an issue. So it kind of like gets stuck. So these are kind of like the non-ideal fix that I had to go through, like setting the data loader to 0 or 1, adding using that AWS recall Fabric plugin so that the communication doesn't get stuck. So yeah, these are the few issues that I faced.